This lesson deals with supplemental problem 813. You can find this problem in the ECE202 ebook in the Chapter 8 Supplemental Problems starting on page 15. In the Lansing area, there are 4 AM radio stations: AM 730, AM 870, AM 1240, and AM 1390. Suppose that we receive a signal from all of these radio stations with the same strength. In other words, the magnitude of the phasor is the same. And suppose that that's 200 picoamps. We're going to have a cosine function with the frequencies of our radio stations. So here's our AM 730, which is 730 kilohertz, 870 kilohertz, 1240 kilohertz, and 1390 kilohertz. Now let's use SPICE to find the voltage across the parallel combination of our AM tuner that we did in supplemental problem 812. We tuned the capacitor to receive AM 1240. Let's also plot the ratio of this phasor voltage to this phasor current, in other words, the input impedance of this parallel combination. As you recall, each SPICE file needs to have a title, so we'll call this AM tuner, and then a dot end. And then we've got 3 elements in parallel between nodes 1 and 0, and I've described this here as R, C, and L. And we have a current source pointing from 0 to 1, so 0 to 1 from the tail to the tip. It's a phasor, so we'll say AC, and then the magnitude is 200 picoamps and the angle is 0. We're going to vary the frequency from the lower end of the AM radio band to the upper end, which is 540 kilohertz to 1.6 megahertz. I'm doing this in a very small range of frequencies, so I'm going to use a different command here instead of decades. I'm going to use what's called a linear spacing. So I'll put 2,000 data points between the first point and the end point. This is very handy when you have a very sharp curve and a very narrow band of frequencies. Let's see what happens to the results. So as I sweep the frequency from low to high, get a response. So given the 200 picoamps that's being applied in magnitude of the phasor, but at this frequency of 730 kilohertz, I only create 0.51 microvolts. At this frequency, 0.77 microvolts. But at this frequency, I've got 200 microvolts, and then at the 4th radio station, I've got 2.5 microvolts. I'll also plot the phase angle, although it's not real critical for what we're doing. As we pass through that resonant frequency, we see a phase shift from plus 90 to minus 90. And right at our tuned radio station, we have a purely resistive circuit, so we have no phase shift. What this implies is that we can now calculate the steady state value of the voltage across the parallel combination by putting the cosine of omega t between the magnitude and the angle. So what you can see here is that we are receiving every radio station, but the AM 1240 radio station is much louder, in other words, larger signal here, than the rest of them, so it drowns it out. If you had a power outage and lost this station, even though you were tuned to it, you'd begin to hear other radio stations. Now let's also plot the impedance looking in. That'd be the ratio of the node voltage 1 to the magnitude of the current source. You can see here we've got a peak in the response at 1240 kilohertz. We have parallel resonance, we get the maximum impedance at the resonant frequency. Now suppose we retune this for AM 730. In other words, pick a different value of the capacitor. If it was a variable capacitor, just be turning the knob to a new value. I use the equation that omega naught squared is equal to 1 over LC. I'm just going to flip these two across. I get 132 picofarads this time. So putting that value in for C, running the simulation again. So you now see at the frequency of 730 kilohertz, you've got a peak in the response. And you get about 200 microvolts. And this is supplemental problem 813.